right, lesson 8.3, task 3. Still looking at compound interest. Model interest compounded more than once a year. Interest may be earned more often than once a year. If interest is compounded n times per year, then the interest rate per compounding period is R over n, where R is the annual interest rate and the number of times interest is compounded in t years is n times t. This leads to the following generalization of the formula. So this is the formula we have already looked at, and if we look at it with compounded for different amounts per year, then we're going to change it to this formula. So n is the number of compounds per year. So you have R over n, and then raised to the n times t power. So the only difference between this formula and this formula is we've added the n, the number of compounds per year. All right, so this says if the initial principal is deposited into an account that earns interest compounded n times per year, then the amount A of money in the account after t years is given by this, where R is the annual interest rate expressed as a decimal. All right, so some common things that you could see if it's compounded daily, there's 365 days in a year. If it's compounded monthly, there's 12 months in a year. If it's compounded semi-annually, that means twice a year. Annually means once a year. And let's see, quarterly. If it's quarterly, that would be 4 times a year. So n would be different depending on how it's compounded. All right, let's look at this example. Lisa deposits $1,500 into an account that pays 4.8% annual interest compounded monthly. What is the account balance after 3 years? How much time does it take for the balance to reach $2,000? All right, so we can see that the initial amount is $1,500. We can see that it's 4.8% interest, and we would have to change that to a decimal, so it'd be 0.048. And then it says it's compounded monthly, so n would be 12. And then it says after 3 years, so t would be 3. So it says to find the account balance after 3 years, substitute the 1,500, the 0.048, which is the 4.8% as a decimal. N is 12 because it's compounded monthly, and t is 3 for 3 years. Plug those numbers into your compound interest formula. Now, remember, anytime you're using a formula, you still have to apply order of operations. So you're going to work inside the parentheses first. So you're going to divide and then add 1. And that's where you get the 1.004. And then 12 times 3 is 36. So you're going to simplify to here. And then when you multiply or when you plug this into your calculator, again, if you do all of this at one time, it should give you the answer, but if you do it step by step, it would be exponential. Do the power first and then multiply. But I think if you plug all of that in, it should give you the answer. So $1,731.83. Actually, now I'm curious. I want to plug that in and see. All right, so if we have $1,500, just want to see what the calculator does here. I think it'll do all of it. 0.004, and then raised to the 36 power. That's going to give us the 1731.83. Okay, good. All right, so you can type all of that in at once. Let's see if you can type this row right here in, if it'll give it to you all at one time. Calculators, very handy, but they're only as smart as the operator. So I'll try different things and see what'll happen here. So let's do 1 plus, and let's put this is division, so let's put this in parentheses, 2 divided by 12. And then I have to close parentheses, and then I'm going to raise that. And then if I go ahead and multiply and put 36, that's fine. But I could also put that in parentheses and do 12 times 3. Let's see if that gives me the answer. It still gives me the answer. So as long as you type that in correctly, do make sure, I'm pretty sure you have to have this in parentheses as well, though, to signify that it has to do this before you add the 1. But anyways, just play with it and see how you can get it to work. All right, so y is n 12. Okay, we already established that it's 12 months. There's 12 months in a year, so that's why n is 12. And it says the account balance after 3 years is $1,731.83. To find the time it takes the balance to reach $2,000, use a graphing calculator to graph the function. And graph the function we were given, and then graph the new function y equals 2,000. Find the x-coordinate of the point where the graphs intersect. Okay, so since they've already graphed this, I'm not going to graph it. You got an exponential function here. Our equation, our exponential growth here that we used. And then there's just a linear equation straight across for 2,000. So where these two intersect, it looks like about 6 years, so just 6.005. So it says, what type of functions do the blue and red graphs represent? So the blue graph is your exponential. Okay, it's just curving up slightly, but it's not linear, but it's curving up. That's your interest function. And then the red graph is just a linear function. All right, so the account balance reaches 2,000 after about 6 years. So you can see where they intersect. The x value is your answer here. All right, that's all for task 3. If you have any questions, let me know. Lesson 8.3, task 4. Model interest compounded continuously. What happens to the compound interest formula A equals P times 1 plus R over N raised to the NT as the frequency of compounding N increases? By letting M equal N over R, you can write the formula as, I'm not going to read that, but it's right here. Okay, so they've just added another variable to the formula. Okay? All right, because R over N equals 1 over M and NT equals M times RT, if N increases without bound, when M will also increase without bound, which means that 1 plus 1 over M raised to the M approaches E. Okay, so we learned about E already. This leads to the following formula for interest compounded continuously. All right, so that leads us to this formula. Okay, so all of this you don't need to know per se. You do need to know this formula. This is just them explaining how we got to this formula from this formula. So it's going to be N increases without bound. So basically talking about your N behavior. If an initial principal P is deposited into an account that earns interest compounded continuously, then the amount A of money in the account after T years is given by A equals P E raised to the RT. So we call this the Pert formula. It's easy to remember if you remember Pert, where R is the annual interest rate expressed as a decimal. So the Pert formula is your compounded continuously function. Okay? All right, so it says estimated trip cost $2,500. All right, to pay for a trip to Machu Picchu in 4 years, Doug wants to deposit money into a savings account that earns 2.9% annual interest compounded continuously. Doug calculates the amount he needs to deposit as shown below. All right, so he's using the Pert formula. E, remember, is a number, 2.7, da-da-da-da. So that's just a number like pi. It's an irrational number. So it's raised to the R times T. R is your rate. So we're going to take 2.9% and change that to a decimal. So move it 2 decimal places. So you get 0.029. And then it says for 4 years. So T is 4. So plug that into your formula, and you want to know when that's going to be $2,500 because that's how much the trip costs. So that's how much you need to have in the account. All right, so again, E is a number, and then you can multiply these exponents together to get this, and then we can solve for P. Okay? So it says 2,500 divided by e raised to this power equals our principal. So $2,226.19. If we have an initial principal of $22,26.19, then we have a compounded continuously formula that will make sure that we have $2,500 for the trip. So Doug needs to deposit this much money into his account and let it sit there for 4 years and compound continuously at 2.9% interest to have enough money for his trip. All right, in the formula for continuously compounded interest, y is the unknown value for this situation, P, rather than A. All right, so P, remember, is your initial value, and we didn't know how much he needed. He knew how much the trip cost, and that's the final amount. That's the total amount that he needs. So that's why we were solving for P this time instead of A. So it's kind of like working the formula backwards, just working for, like to set his goal on what he needs to do to save money. How would the amount of money Doug needs to deposit change if his account earns interest compounded yearly instead of continuously? Well, if it earned interest compounded yearly, then you would have to use the original formula up here, and you would still have to solve for P, and then you may have a different principal that you have to start with instead of what it was. So it says, how would the amount of money Doug needs to deposit change if his account earns interest compounded yearly instead of continuously? Doug would need to deposit how much money? All right, so let's look at this formula up here and see. All right, so let's look at this other formula. I had to get my pen, so now I've got my pen. So let's look at the original formula, because now we want to see how much Doug needs to deposit if compounded yearly. So we're going to use A equals P times 1 plus RT. So we know that we need $2,500 in the account. That's how much the trip cost. And we're looking to find a principal. And the interest rate was, I think, 2.9%. Yes, 2.9%. All right, so 0.029 and for 4 years. All right, so to solve this, we can divide by 1.029 to the 4th power. Divide this by 1.029 to the 4th power, and that would give us our amount. So let's see what that amount is. So if I pull up my calculator here, I'm going to do 2,500 divided by 1.029 raised to the 4th power, because we're looking for 4 years. So that would be 229.86. 229.86. $2,229.86. All right, let's see if I can get that in there before time runs out. So 229.86. So that's how much he would have to deposit if he used the different formula. All right, if you have any questions on compound interest or compound continuous interest, please let me know.